people. Hope we're doing well today. Yesterday in class, I tried to explain sort of the rationale, the logic behind the integral test error calculation formula. And I tried to explain it to you in two ways, and I think because of that, it came out a little bit muddled. So I tried to figure out how best to streamline the information, so let's just go through it again, okay? Now, remember that our discussion involves partial sums, and of course, partial sums, you're dealing with infinite series, which are a sum of an infinite number of things. A partial sum, of course, according to the name, is a sum of part of it, okay? Now, if that is my series for my a sub n, then my partial sum, my nth partial sum, is basically the sum up to the nth term. Now, that of course will be an approximation for the whole if it is a convergent series. And basically, it may not be a great approximation, but it's an approximation nonetheless. What we need to calculate, of course, the question that comes after you make this approximation is, okay, well, how good is the approximation? And that's the entire point behind all of this. Now, remember that if we have a true sum, okay, and a true sum would be the sum of the entire thing. So the sum of this entire thing is your S, okay? And that is what this S is. So if you basically subtract the partial sum from the actual sum, you're going to get some leftover, right? Some remainder, hence the R. Now, the remainder is all the terms that are left, right? Basically you chopped off right here in order to get this is basically this, okay? And basically the rest of it out here, right, is your R sub n. That makes sense. It takes a little getting used to because we're used to this subscript referring to something in the series itself. You simply have to remember for remainder, what that means is the remainder, if it's S sub 8, then R sub 8 is the remainder associated with S sub 8, but actually starts at the 9th term. So that n plus 1 is going to be pretty important. Now, remember I've been likening these sums to Riemann sums, which they can be. They can be expressions of Riemann sums, because remember that's the last place that we saw sigma notation. Now, if I think about it that way, then of course I'm looking at Riemann sums that necessarily have a subinterval width of 1, right? Because when I'm dealing with series, or when I'm dealing with sequences too, I'm only interested in the integer input, okay? So let's go ahead and move on to the next page. Now, the sum, of course, has a particular relationship to the improper integral. Now, we recognize that when we actually did the integral test. Well, that relationship is still there and actually impacts how we calculate, how we wind up calculating the error, okay? And here is how the relationship works. Now, before we actually get to the specific relationship, we need to remember that R sub n is the remainder left after the nth partial sum. So it begins at n plus 1. Okay, so its relationship will be with the improper integral. That also begins at n plus 1. Okay? Okay, but let's go ahead and make it a little more concrete. Let's say, just for giggles, that basically I was looking for S sub 8. Okay? Okay, and I'm looking at this, I'm basically using this, and I realize that what I need is the 8th partial sum, and let's figure out from the 8th partial sum what my remainder should be. What my remainder should be. And the thing is, I'm not going to get it exactly, but I'm going to get it in the neighborhood. Now remember that if it's S sub 8, then what I'm worried about, those first 8 terms were, of course, the one that's up here, plus this number, 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 because this right here is 8. Okay, so this portion over here basically are the values added together that make S sub 8. The values out here are going to be what makes R sub 8, the remainder. It's going to be this point, and this point, and this point, and this point. Now, I stretched it a little in order to be able to see it, but that value right there, if I simply multiply it by a width of 1, is going to be the same as that area right there, right? And let me zoom in. I tried to do it so that we could see it a little bit better, but it still gets pretty flat right there. Okay, and then of course go over here, okay, and you have this sort of infinite Riemann sum all the way out, okay? Now, here's the key to all of this. You obviously know, okay, that the Riemann sum, R sub n, okay, has a relationship to the integral, okay, this integral. So if we were to say, you know, R sub 8 has some relationship of 9 to infinity of 1 over x to the 3/2 dx. What is that relationship? Well, that relationship is right here, okay? Because you know that if it is a decreasing function over that interval, that a left-hand Riemann sum is going to be an overestimate. Okay, well, as we said before, we're trying to sandwich this estimate between two values. So if R sub n is an overestimate, meaning the area under this curve will be less than the Riemann sum, the remainder of the series, then it stands to reason that we need another integral in order to show the relationship of the Riemann sum being an underestimate. Okay, so let me walk through that again, and let's just go ahead and read it right off of here. Because the Riemann sum is a way of conserving the series R sub n. Because the Riemann sum is a way of, gosh, that was an autocorrect right there, of basically representing our series R sub n, it has a uniform subinterval of width 1. This means that we only need to move the given function to the right by 1 unit in order to transform the overestimating left-hand Riemann sum to be transformed into an underestimating right-hand Riemann sum. And let me show you what I mean by that. Now, I'm going to do more than just the points that are associated with the R sub 8. I'm going to show you that just the Riemann sum in general for this function is going to be the left-hand Riemann sum of this term over here, right? Of this function over here is going to be the underestimate of this, because they're exactly 1 unit apart, okay? And so if I actually have this point right here at 2, and I were to draw it across in order to make my rectangle right here, notice that the height that was determining the height of that rectangle, that subinterval, it is a left-hand Riemann sum rectangle with respect to this one, but it's a right-hand with respect to that one. And the same is true here, okay? Okay, and here, and here. And so it's definitely true out here for the, you know, R sub 8, which starts at 9, okay? And so basically this Riemann sum, because the height at the left for a left-hand Riemann sum for this function and the height at the right for a right-hand Riemann sum for this function are the same height, you can recognize the fact that that Riemann sum is going to be an area that is sandwiched between those two functions. Now, we need to go ahead and at least start off by thinking of it as, of course, that x minus 1 is the, so if you have, you know, y is equal to 1 over x to the 3/2, you know, if this is y1, y2 x minus 1 to the 3 halves is, of course, a shift to the right of 1, right? Okay, well, if I shift it to the right 1, that n plus 1 and that x minus 1, once I actually do my integration and start plugging in and actually resolving this improper integral, that plus 1 and that minus 1 are going to cancel out. So actually this winds up being equivalent to this. Notice that the only difference here is that n plus 1 became n at the same time that x minus 1 became x. Those wind up being equivalent, okay? Because just think about the process of actually plugging them in after you do the integration and before you actually execute the limit. Now, what that means is because you've sandwiched that Riemann sum between those two graphs, you know that that remainder series, which of course is equivalent to the error from the partial sum, is sandwiched between those two values. So all you have to do is actually evaluate both of those improper integrals, and of course the actual integration part, the analytic part, is the same. It's just a different number that you're going to be plugging in. They wind up being equivalent, okay? Now, that's basically it. Now, if we want to make it sort of general for all functions, we just have to take it from the 1 over x to the 3 halves and transform it into just f of x, like any f of x, okay? Now, if we are given the fact that that is the case, okay, you need to remember that r sub n at that point is going to be s minus s sub n. And then if I want to actually figure out, because I know what the error is sandwiched between, I can figure out what the actual sum is sandwiched between just by adding s sub n to all three pieces of that original inequality, okay? That is what I was actually trying to get at yesterday in class. To the extent that I actually accomplished it yesterday in class, yay. To the extent that I didn't, ignore yesterday. This is the video that you need to be paying attention to. Of course, the actual example that we did winds up being, because we actually ran it through the correct formula. The example that we did and the numbers that we arrived at are all absolutely correct. It was just the muddled presentation of the justification and the rationale, the logic of that formula that I thought was a little bit lacking. So, if you have any questions, please do shoot me an email. Bye.